So, we've been talking a lot about chain rule. You probably feel like you've chain ruled enough, but we're not quite done yet. Today we're going to spend a third day learning about chain rule. And in this day, we're going to look at some of those hard problems again, make sure we can do them, but more importantly, we're going to use chain rule as part of a problem where our goal is to get like a tangent line or a secant line. So number one, find the slope of the line that is tangent to this curve at the point where x is pi over 3. As soon as I see tangent line, I know that I need a point and I need a slope. Now they give me the x value of the point, which is pi over 3. To get the y value, I'm going to take that and plug it in here. On the unit circle, the ordered pair at pi over 3 is 1/2 comma root 3 over 2. Sine would be the y value. So if I do the square root of 3 over 2 to the 5th power, I get a square root times a square root times a square root times a square root. So 9 root 3 over 2 to the 5th power is 32. Now to get the slope here, I'm going to need to use a derivative. So what I find helpful is to rewrite this problem as sine to the 5th power. If I do that, I find it much easier to recognize that there is a chain rule problem here because that 5th power is around the entire sine function. I'm going to leave the inside alone and I'll multiply by the derivative, which would be cosine. Now if I take that function and I plug in pi over 3, and make sure you're using the correct notation here, y prime of pi over 3, I get 5 times the sine of pi over 3 to the 4th power times the cosine of pi over 3, which means I get 5 times sine of pi over 3, we said, was the square root of 3 over 2 to the 4th power. Cosine was 1/2. The square root of 3 over 2 to the 4th power would be 9 over 16 times 1/2, which gives me, let's see here, 45 over 32. Now if I go back to the original question, they never actually ask me to write the equation of the tangent line. All that they ask me for is the slope, so I'm done. Now here it says, show that the slope of every line that is tangent to this curve is positive. So we're trying to look at the slopes of the tangent lines and show that they're always going to be a positive number. To do that, we need to look at the derivative. So, let's take the derivative. I'm going to rewrite this as a problem that is to the negative 3rd power. To me, that's just easier. And I'm going to leave the 1 minus 2x inside. Oops, this is just regular old y, sorry. So now the derivative would be negative 3 something to the negative 4th power. Leave the something alone times negative 2, which is the derivative of the inside. If I simplify this, negative 3 times negative 2 would be positive 6. And I'm going to go ahead and relocate the 1 minus 2x to the 4th power back to the bottom. Now let's think about this for a second. A 6 is always positive. A 4th power is always positive. Therefore, a positive divided by a positive would always be positive. So we just showed that every slope here is going to be a positive slope. And we're done. On the next page, let's look at some complicated chain rule examples one more time because we want to be really good at this. So For the first problem, we're going to need to use product rule. Copy the first, negative 3x to the third minus 4, times the derivative of the second, so negative 4x cubed, plus copy the second, negative x to the fourth minus 1, derivative of the first. I like to think about this as being negative 3x to the third minus 4 to the 1/2 power. So I would drop the 1/2, leave the inside alone, change it to a negative 1/2 power. Negative 3x to the third minus 4 times the derivative of the inside would be negative 9x to the second power. Now if I just rearrange this a little bit, I have negative 4x to the third times the square root of negative 3x cubed minus 4. Now I'm going to take the negative 9x squared and the 1/2, and I'm going to make them coefficients. So instead of a plus sign, I'm going to have minus 9 over 2x squared times negative x to the fourth minus 1. And this negative 1/2 power is going to move to the denominator and become a square root. Now, one last thing that we can do here to make things look a little bit prettier. We have a denominator here. We have a denominator here. So we can just put them in the same denominator. So negative 4x to the third square root of negative 3x cubed minus 4 minus 9x squared times negative x to the fourth minus 1 over 2 square roots of negative 3x cubed minus 4, and you're done. So I just took both of those denominators and I put them down here. See the 2 and the square root. Okay, we're going to save number 2 for tomorrow in case we need an example to go over in class. Let's jump down to number 3. This one will require us to do quotient rule. So we would do low, which is negative x squared minus 4 to the negative 5, d high, which is 3x squared, minus high, which is x cubed plus 5, d low, which would be negative 5, leave the inside alone, change it to a negative 6. This is a negative x squared minus 4 times negative 2x. And low squared goes down below. Now let's simplify. I'm just going to move the 3x squared to the beginning. I'm also going to take this negative 2x and this negative 5 and move it to the beginning. So negative times negative makes it a positive, which means when I've got a minus, a positive, it's just minus. Now on the bottom, I'm going to distribute this 2, and I'm going to get a negative 10 power. Now you'll notice that this and this and this are all the same. And we've got a negative 5 power, a negative 10 power, and a negative 6 power. So what I'm going to do is I'm going to cancel some stuff here because all 3 terms have the same stuff. So I'm going to cancel 5 of them. I'm going to cancel this 5. I'm going to have 1 of these left over, and I'm going to have 5 of these left over. Which means my answer is going to be negative 3x squared minus 10x times x to the third plus 5 times negative x squared minus 4 to the negative 1 all over negative x squared minus 4 to the negative 5. And we're going to leave it just like that. Again, number 4 is a quotient rule problem. We will save that one for tomorrow just in case we need another one to go over. As you can see, chain rule does get a little bit complicated, but hopefully you're starting to see some of the pattern and that the real struggle is more in simplifying than in actually doing the derivative. Okay, we're good.